on your Moodle web page, so you can have access to these slides. There are some reading materials which are assigned to you in the course outline, so you can consult those texts for the detailed definitions and theorems. Also, there's a lot of material on the internet now, which was not there 10 years back. If you have a particular word and you do a keyword search for that, Google gives a lot of materials, so you can learn from the internet. Also, the library has quite a few online books on topology and differential geometry. Topology is an important branch of mathematics as well as differential geometry. So you will find online texts in the library. And I would urge all of you to read different versions of the same axioms and theorems and definitions. Some texts have different examples to solve. So this is a big sphere of knowledge which opens up. And it's not like physics where there's one equation and one set of data to describe the same system. There are different ways of presenting the same math in different texts. So there's a bit of subjectivity, and you can score your own set of notes based on the wide variety of books on topology and differential geometry, as well as lecture notes on the internet. Now, to put the module in perspective, we physicists deconstruct the universe. The physics as a science, as a stream of science, is the study of matter and its interactions. And natural phenomena is, however, very complex, and we try to capture all the phenomena using mathematical equations. But physicists are famous for deconstructing the complexity into simplified, idealized descriptions. In particular, all the visible matter and its interactions is categorized into the physics of a set of objects which live in the representation of SU3 cross SU2 cross U1 Lie groups of symmetries, and their mutual interaction happens because nature tries to preserve these symmetries. Now, stated like that, without the mathematical description of the structure of these Lie groups, it really doesn't make sense. To a person who wants to understand nature, SU3 cross SU2 cross U1 has nothing to do with the snow on the tree outside. But it turns out that that is what nature is. And this is all mathematics. The structure of the Lie groups and the representations of the particles is a mathematical construct. And it is very, very surprising that all of visible matter and its interactions is described by this set of Lie groups. Why not SU5? Why not SU10? What about, other symmetries of nature? So that is something which physics has achieved in deconstructing nature down to its fundamentals. And what mathematicians have given to us is the structure of Lie groups. So we want to understand what this is all about from the point of view of the mathematics of this system. But these visible matter and interactions live on a background. And this background is what we call the space-time manifold. So you've probably heard the word manifold a number of times. You've studied general relativity. And this manifold has its own dynamics, which is the general theory of relativity. And the entire existence of us is hinged on this theory of gravitation and the evolution of cosmology, which requires, in addition to the 4% visible matter, the dark energy and dark matter, which we haven't yet observed experimentally. So there might be something wrong in our mathematical construct, and learning the basic premise or the basic structures of these mathematical equations might, help us realize the actual description of nature, which might not have anything to do with dark energy and dark matter at all. Or if it has, then it might lead us to the true nature of dark energy and dark matter. So, the uh, indirect evidence we have for these dark energy and dark matter, which is about 96% of the universe, uh, is something which we have to understand and comprehend for us to be sure of what our structure reality is. Now, therefore, what we have to understand is, first of all, the manifold, the space time, what we imagine as the vacuum in which natural dynamics happens. In mathematical notation, and we use it all the time in formulation of gravitation and the theory of general relativity, is a pseudo-Riemannian uh, geometry. Topologically, it's R cross sigma 3. So we use this already in our understanding of general theory of relativity and the theory of gravitation. What is space-time? It's R cross sigma 3. That's a very compact way of basically putting all that we see around us into a mathematical symbol. Philosophically, space time is something which accommodates
Question?
matter. Yes, shall I stop the recording or
No,
you?
no, it's okay.
Okay, go ahead.
That R means the real number. This is time. It represents time.
Yes, I will. Yes.
Okay,
Okay.
thank you.
Um, that's why it's pseudo-Riemannian. And I'm assuming that you have a background in general theory of relativity as well as set theory. That is what we will invoke now to understand what a manifold is and what is the background in which we formulated the dynamics of uh, particles and matter, uh, the interaction gauge fields, and so forth. So now, you've already seen this, but what is this manifold on which we describe our dynamics? This draws from a mathematical construct known as a set. But not all sets are manifolds. For example, if I take the set of the trees in Lethbridge, that is not the space time on which we formulate the dynamics of our particles. Our space time is an abstract set from the point of view of our visual perceptions or our senses or our consciousness. And it's very much hinged on the mathematical formulation of a manifold. So we have to learn what a manifold is, and then we formulate the dynamics of the particles and the interactions on that manifold. topology is the study of points. Topology precedes the formulation of a manifold, but we require topology to understand the manifold and the space-time arena. For example, topology will teach you how to distinguish between a orange and a donut. What is the difference between a sphere and a torus? This is a simple question. Are they same or are they different? From the point of view of mathematics, they are different. Or if we take the letter X in the English alphabet, is it the same as the letter Y as a collection of set of points which make the topology of the system? Now we want to understand a collection of points using some aspects which will tell us how to classify or structure these points. Why? Obviously, there are some deeper questions which we would like to eventually answer. And that is what is, for example, the nature of our space-time, of our universe. Is it topologically simple? Is it topologically complex? In fact, whether it is like a donut or it's like a sphere. So the eventual answers which we are seeking are very deep and very real. They're not imagined, but the construction or the structure on which these questions are based on is totally human in origin. So it's from our heads, our conscious thinking, that we are structuring the human language, and then we hope to answer some questions about the reality using these structures. Next, why are we studying differential geometry? We are studying differential geometry because obviously, once we are aware of the topology of the universe, we would like to understand if the geometry is curved or if the geometry is flat. So, given the notion of distance or metric on a manifold of a given topology, we'd like to do calculus of the system. So, in some sense, from global to the local. And this information is structured into a field of mathematics, which is known as differential geometry. So, after we've understood topology, it's natural to understand the differential geometry of our space-time arena. And we know that why we have to understand curvature, because we have experimentally verified existence of bizarre geometries like the black holes, and we have real images of the existence of a black hole horizon. And it is there that we have high curvature systems. So we want to formulate the calculus of manifolds or the calculus of a set of points in a formal way so that we have some expertise or hold over these, and then we can formulate reality in terms of the structures. There's also causality involved in the definition of the horizon, but we will not include causality in these discussions. We will just use the topological aspects and the differential geometric aspects of manifolds in these discussions. Now, this is food for your thought. What aspect of mathematics would the notion of causality talk to? Is it purely physics? or there is some mathematical structure in which we discuss causality. Now, obviously, Lie groups and Lie manifolds, which is the next topic of this module, is equally important because after we formulated the background structure, we have the dynamics of particles on the background structure, and they are totally described by the Lie symmetries. And these symmetries live in some abstract space. All the particles and the mediators of interactions, the gauge fields, are representations of these groups and their symmetries. And because they are abstract, we don't see them visually in our conscious existence, but they are real. And the way we describe these symmetries as if we have a base manifold, and at each point on the base manifold, we have a fiber, which is an abstract fiber, and the symmetries or the Lie symmetries, the SU3 cross SU2 cross U1 symmetries live on this fiber. The fiber bundle, which is the net description of the base manifold and the symmetries of nature, comprises of the base as well as the fiber. So it's like a comb structure, and it's important to understand this nature of our reality, where the base manifold is something which we can measure and describe using coordinates, and the symmetries live on fibers attached to these base manifolds. And when we have different gauge transformation related or SU2 or SU3 or U1 related configurations, they all are different sections of these fiber bundles. These fibers are abstract, but the manifestation of their existence is there in the base measurements. So our dynamics is on a fiber bundle from what we have formulated up till now. Of course, tomorrow something might happen and all the construct we have might just crumble into totally something different. But till today, this is what we have as the description of nature, and this is what we learn in this module in from the point of view of a mathematical physicist. Okay, so the first topic which is there for today is topology. So we will start with the notion of topology. Now here I will draw on your current perceptions of what might be topology, and then we will build upon that. Now, the basic premise or our structure is a set. So there is a set. By definition, mathematically, it's a collection of objects. A set can be empty. I remember someone gave an empty set definition as the set with elephants who can sing. Obviously, I don't know if elephants can sing or not, but according to that person, that was an empty set. But what it means is that it has nothing in it. Empty set is a set with no elements in it. Then we can build set of numbers. In particular, our favorite set is the set of real numbers, which we write symbolically as R. So that's a typical mathematical notation for the set of real numbers. This set has infinite elements in it, but there is more to that set of real numbers. Why we are interested in real numbers? The real set is actually one of the first descriptions of what we have to eventually describe, that is space-time. So one Euclidean dimension is the real line, and that's described by the set of real numbers R. Now the questions we want to ask on this set of real numbers is, for example, is the number 2 or is the element 2 near the element 3? Is the element 12.01 near 100? And all of you can quickly do this calculation. There is a notion of distance on the set of real numbers. The set of real numbers is a set which is known as a metric space. It has notion of distance. It's also known as the norm, and it is a map, mathematically it's a map from the product space of uh, X and X. So we usually label the set which we are analyzing as X. So X times X to the space of real numbers. So it takes two elements from a set and maps it to a real number. That's known as the metric function on a given set X. So you can generalize the notion of distance to arbitrary collections of mathematical objects. And this map is restricted in such a way that d of xy is equal to d of yx, and d of xy is greater than equal to 0. It is 0 if and only if x is equal to y. And then there's the Cauchy-Schwarz inequality. Now, all of you know that the distance on the real line is simply implemented as, oops, can you still see the screen?
Yes, but no slides.
Okay, are the slides back?
Yes.
Okay. So the notion of distance on the real line is simply modulus of x minus y. That is a definition which satisfies all these three criteria, and it's a map from the Cartesian product of the set of real numbers to another real number. When d of xy is less than a particular pre-assigned real number, then we say that these two are near. And if it's bigger than that pre-assigned real number, we say it's far. So the notion of nearness in the set of objects is defined using metrics, and all of you have seen this in real life. Let's say when we say Calgary and Lethbridge are near compared to Calgary and Edmonton. So there's also this measurement of distance when we locate ourselves on Earth. We could also put a reference frame in space, and then we could measure our location with respect to that reference frame. And we have our notion of distance in the sense of a metric. So our Euclidean space is a metric space, but that is not where we start. For the mathematics of topology, we start with the set of objects without metrics. So we want to have the notion of nearness, or the notion of being able to classify two objects in a set or two elements in a set as being close or far without the definition of a metric on it. That is where we start. We are not totally wild, so it's not a collection of elephants or a collection of trees. It is a collection of elements or a set of points on which there is a structure. But this structure is pre-metric, and that is where we start the story of topology, which will take us eventually to metric spaces and differential geometry of manifolds. So topology is more general than the metric space with which we usually work in. And the notion of topology, which were global, like the difference between a sphere and a donut, or if we live in a universe with a wormhole, or just expanding sphere, that is answered using the topological structures by itself. We don't have to zoom into the local, find curvature or parallel transport, the concepts of local changes in metrics or differential geometry to answer questions about topology. So those questions can be answered in pre-metric spaces, and those are known as topological spaces. Topological spaces, we will answer questions about compactness, connectedness, separability, and path connectedness of any two elements in that set without using the notion of distance. Once we have a metric space, then we will start with differential calculus. So is it making some sense? What is topology? So topology is about some aspects of these collection of elements in a set, and these can be answered without introducing the metric. So we are talking about distances in some sense without defining the metric or without norms or inner products. For these, we use what is known as convergences of sequences. Neighborhood of an element of a set is a collection of subsets of X, which is labeled as this curly nx. So given X, an element in a set, capital X, we have a collection of subsets of X, which we label as nx. And these collection of subsets would be a neighborhood of X because they are in quote and unquote the neighborhood of X, or they are near X. How do we identify or how do we define this neighborhood or nearness? This is using a sequence and convergences of these sequences. If we don't have that structure, then obviously we won't have any sense at all. So if we don't have this convergence of sequences, then that set cannot be discussed using these techniques. So for all n, which is the set in the collection nx, there exists a n naught such that for n greater than n naught, the sequence xn is in the set n. So we're given a sequence of elements x1 to xn. If there exists a n naught, a way of enumerating the elements of the sequence, if there exists a n naught such that for n greater than n naught, sorry, I have to say something. So now we are shifting to logic and actions. So till now we were talking about things which we can visualize or describe. Now we are shifting to mathematical formulations of these neighborhood spaces. and that is based on logic. So this is pure logic. If for all, so these things are very important. The word all. It could be different if we had used the word any. So you see, these wordings are carefully crafted, this mathematical structure in each of these words. If we had used for any n, then it would be a totally different logical description of this system. But here, it's crucial that for all n, which is a subset in the collection of subsets n of x, there exists one integer n naught such that for n greater than n naught implies xn is in the set n. So there is a sequence which is converging to the subsets n, and for all the subsets n within the neighborhood space of x. And mathematically, we say that xn sequences converge to x under the neighborhood set nx. This is a logical way of saying that all sequences converge to x via the collection of subsets n. If we can find such sequences, then this neighborhood set is called a neighborhood space. It takes a little bit of time to absorb all the implications of what this is saying. But if we draw a visual picture of this, if we represent a visual picture of this, this would be starting from some x1, and then slowly as the elements of the sequence x1, x2, x3, x4, x5, etc. are progressed, we will find the xn when n is greater than n naught within the collection of subsets n. So we can visualize this meaning in the manifold description. I will bring up a whiteboard in case this is seeming too abstract to explain what this is. So we can see this. A manifold obviously has a notion of metric and notion of distance on it. But imagine that this is just a collection of points, and one of the elements of this set is x. Then this is nx, a subset of the bigger set, and it has collection of subsets. Then if we start anywhere here with element x1, we can define sequences such that for all the n's, there exists a n naught. For this n, it could be n equal to 5 or n equal to 6, that we end up in the 7th element in this set. This could be, we start at x1, x2 in this region. Let's say at x4, we are already in this set n, and so forth. Then if we can have this collection of these set n's, this capital N set, they would comprise a neighborhood of x. Does it make sense? So there exists a n naught, a particular value of the labeling of the sequence, after which the elements of the sequence end up in a subset in the collection Nx. Then we say that Nx is a neighborhood of X, and the space capital X and Nx is a neighborhood space. So here, the notion of distance or nearness is replaced by the sequencing of the elements in a set Now we come to the notion of closed and open sets, which is again crucial in the definition of a topological space. For this, we need the definition of an interior point of a set. The interior point of a set A, which is a subset of the bigger set X, which we are analyzing, is any point small x such that there exists a subset capital N in the neighborhood space Nx, with N being a subset of A. So this is the notion of interior point. Again, we can take our favorite manifold set and then we can visualize an interior point X and test this definition for a general abstract collection of elements X and a subset A of that X. A boundary point of a set A, which is a subset of X, is any point X such that it is both in A and in the complement of the set A. That is the boundary point of a set A. An exterior point of a set A, which is a subset of X, is any point X such that X is entirely in its complement. So a set and its complement is a well-defined concept in set theory. So as I said, one of the basic premises I'm assuming is that you have knowledge about set theory. In particular, A and A complement union is X, and A complement intersection is the empty set. So all these notions, I hope you already have in your head. And we are using these notations, like this is the subset notation. This is the in or belongs to notation. These are all from the set theory, description of systems, and set theory is one of the basic mathematical courses which you learn. So I'm assuming that all of you are familiar with these notations and these definitions. Now we have the definition of open set. A set A is open if and only if A complement is closed, or in other words, the set A is equal to the collection of its interior elements. So A is equal to interior A is the definition of an open set. You can also rephrase this: A is open if and only if for all X in A, there exists a set N in its neighborhood space such that N is a subset of A. Again, this is a collection of all points in the interior of the subset A. If a set is equal to its interior elements, then that set is said to be open. And you are familiar with this in the description of manifolds, as well as, let's say, the real line. The open interval from 0 to 1 is an open set. So without using the boundary point 0 and 1, we have the open set that's known as the open interval because it has only its interior points. Now we are ready to define the topological space. So we introduced the concept of a neighborhood space, And now we will introduce the topological space. The topological space is more than a neighborhood space in the sense that a topological space is a neighborhood space Xn. So X is the set and N is the set of all neighborhood spaces for all its elements X, in which for all X in capital X and for all capital N in the neighborhood space of X, there exists one N1 in Nx such that for all Y in N1, N is also in the neighborhood of Y. So topological space is a more structure than a neighborhood space because it says that if there are points in the neighborhood of X, so let's say we have this Y, then there should be at least one set in the neighborhood of X, which is also in the neighborhood of Y. So sufficiently close elements to element X should be also in the neighborhood of X. And vice versa, sufficiently close points to Y should be in the neighborhood of Y. So it can't be totally wild that the neighborhood of X and neighborhood of Y are totally disjoint. Then that's not a topological space. So there is more structure than a neighborhood space because the topological space talks to the elements in the neighborhood of X. And there should be an overlap between the neighborhood of X and neighborhood of Y. At least there should be one set which is both in Nx and Ny. Then that set we call the topological space. Then that neighborhood space we call the topological space. This definition of a topological space is due to Isham, one of the textbooks which we are closely following. And this notion of nearness, which we defined using neighborhood space and sequences, gets now supplemented with this notion of neighborhood elements nearness. And this also leads to the concept of open set. The concept of open set. We can ensure that this restriction is implemented if we have neighborhoods of open set. If we have closed intervals, then those intervals can be disjoint. But if we have open set intervals, let's say we visualize this on the real line, then this notion of being closed gets implemented. That is why we had to introduce the definition of an open set to bring in the definition of a topological space. Now, the usual definition of the topological space, which would be definition 1 of this lecture, is based on this open set structure and this notion of nearness, which we tried to capture in the definition due to Isham. It says, let tau be any family of subsets of a set X that satisfies the 3 conditions. The empty set and the entire set X belong to tau. An arbitrary union of elements of tau belong to tau. Any finite intersection of elements of tau belong to tau. And if this collection of tau, which are subsets of X, satisfy these 3 criteria, then we say that tau is a topology on X. So the stuff which we were visualizing for a manifold, when it's implemented logically on an abstract set, it is these 3 axioms which ensure that those visual concepts are realizable in this abstract set. Now we'll see it in a minute in an example. And we'll take a simple example of a discrete set to see and implement topology. If we have a discrete set, let's say X is A, B, and C, so 3 elements of the English alphabet, this is known as a discrete set. It's not a continuum set like the real number, set of real numbers. It has 3 elements, but we can see the implementation of the same notions of neighborhood space and topology on this discrete set, and then it becomes a little bit more easier to absorb the abstract concept of topology and a neighborhood space. Now, when we have discrete set and we build subsets of this discrete set, then those are basically technically both open and closed. So if we have a subset A or AB, then that is both open and closed. So that's why we can still use the concepts of topological space implemented and implemented on this discrete set. So if we are given this set X and we want to build a neighborhood space, then we could define NA equal to the collection of these two sets, AB and X. This is a neighborhood space of the element A. X is the entire set. AB is the collection which has A in it. This would be a bona fide neighborhood space for this discrete set for the element A. But that's not a topology.
I have one question.
Yeah.
Why is C not in the neighborhood space?
Because C does not have A in it. C and A are two disjoint set elements. X has A, B, C, all 3 in it. And then AB is the other set which has both A and B in it. We could also add just the set A to it. That would also be a neighborhood space. But this is one example of a neighborhood space.
Okay, thank you. So C is not close to A because it's not.
Right. It's not, if we define just the set, a set with just C in it, then that would not be in the neighborhood space of A. It will be in the neighborhood space of C. Does it make sense?
Yes, that makes sense.
Finding the neighborhood space of A, and if we include just the set with C in it, it obviously would not be in the set of elements which approach A, right? C is disjoint, different from A. Okay, so if you look at this set N, label this as capital N, one of the notations which we used, then it has B and A. Obviously, the second element is the element A. So this is in the neighborhood space of A. In the ABC, if we count, let's say from C, then the third element is A, right? So these two are in the neighborhood space of A. Okay. Now, if you want to define a topology on X, that is not the same as this, because the topology from the 3 axioms which we use to define the structure comprises of a collection of subsets of X. This was also a collection of subsets of X, but this was not a topology. It was a neighborhood of A. Here we have a topology on the set X. Tau is the collection of subsets of X, which has the empty set, the set X itself, AB, and A and B. Remember, a set is its own subset, unless we put some further restrictions. Why is this second example a topology? Because for that, we have to test it for the three axioms. Oops. What is the three axioms? Empty and X belong to tau. An arbitrary union of elements of tau belong to tau, which means union of the subsets are also in tau. Finite intersections of the elements of tau belong to tau, not infinite. Finite intersection of the elements of tau belong to tau. We're seeing these three axioms as implemented on a discrete set so that we see these easily implementable. But of course, if we use, let's say, a manifold set, then we have to ensure that these subsets are open subsets. Okay, so here we have this tau as being claimed to be the topology on X. How do we verify that? So the first axiom is satisfied, the empty and the X are included in tau. Next axiom is that all the unions of the subsets of X should be in tau should also be in tau. So if we take a union of X with empty, it's X. If we take a union of X with AB, it is ABC. So that is also in here. We take the union of AB with A, that is AB, that's also in here. If we take the union of A and B, that's AB, that's in here. So all the unions are in this collection. Now the intersections also have to be in this collection. Intersection of empty set with X is empty, so therefore that is there. Intersection of AB with A is A, that is there. Intersection of AB with B is B, so it's there. Intersection of X with AB is AB, so that is there. So we checked all the elements of this collection and we verified all the three axioms, and therefore it is a topology on X. Now, for you, examples to be solved now. So take a pen and paper or just do it in your head. Does this collection of subsets tau form a topology on X? Do they define a topological structure on X where X is a discrete set comprised of 5 elements? Does tau define a topology on X? Next, does tau1 define a topology on X? I'll pause the recording. Next, what we will learn before we start the concept of compactness, connectedness, and separability is the concept of homeomorphism. When are two topological spaces equivalent to each other? That is one of the questions we want to answer, whether the sphere is the same as a donut or whether the sphere is same as a torus. And to answer that question, we saw that we need some structure, and that structure is the structure of a topological space. We just introduced that structure in the previous 2 slides. Now we want to formalize the question by defining what is known as a homeomorphism. A homeomorphism is a map F between two topological spaces, X tau and Y tau prime, if F is a bijection, which means that the map is 1-to-1 and onto. So all the elements of X tau are mapped to unique elements of Y tau prime, and there is no element which is left and that is not being mapped. So there's no extra elements. All elements of X tau are being mapped to elements of Y tau prime. So that is onto. And each element of X tau has a unique image under the mapping in Y tau prime. So it's 1-to-1 and onto, that's known as a bijection. And then this map and its inverse are both continuous. So that is the two requirements of a map which makes the two topological spaces homeomorphic to each other or equivalent to each other. And then we can ask this question, is X topologically equivalent to Y? Why is this equivalence relationship? Because it has all the elements required in mathematical language for equivalence, and that is, it is reflexive, it has symmetry, and it is transitive. What does it preserve under these maps? It preserves compactness and connectivity of the topological space, and therefore we'll introduce this eventually. What is equivalence relation? This is a cup morphing into a donut. So a cup is same as a donut topologically, but a sphere is not. So we'll see in a minute why it's not. So reflexive is when A is equivalent. When we define a map, then reflexive is the property of the map which says A is mapped to itself. Symmetry is when A is mapped to B, then B is also mapped to A. And transitive, when A is mapped to B and B mapped to C, then A is also mapped to C. So when a map has all these three properties, then we say mathematically that these are equivalent to each other. Now this GIF taken from Encyclopedia Britannica shows that we can map a cup to a donut topologically. These are equivalent. They are the same manifold. I can use the word manifold because these are manifolds, but these are same set of objects. They have the same topological structure because one can be morphed into the other. Now we'll see in a moment what is preserved under this homeomorphism or the map which has these three properties and what is not. So we said that the notion of compactness is preserved in a homeomorphism. So basically what this means is that we can characterize a topological space with the notion of compactness. We can characterize or classify topological spaces according to whether they are compact or whether they are not compact. Now, as I can see, I have about 5 minutes left. So instead of going into the definitions in details, I will just, give some examples of a compact set. And then we'll come back to these definitions using accumulation points, and then cover sets and subcover sets. So an example of a compact set is this compact interval 0 to 1. So when the boundary point is included, this is a compact set. When the boundary point is not included, this is an open set and it's known as a non-compact set. Then we will discuss separability, which is something probably you have seen quite often in papers with Hilbert spaces. Hilbert space of a particular theory can also be classified as a topology, can also be classified as a Hausdorff space. So Hausdorff is a word we use quite often. The Hilbert space of this is Hausdorff. What does it mean? So we come to these concepts, and then we will take up connectedness, in particular path connectedness, which we'll come back to when we talk about homotopic groups and DRAM cohomology, is something which you can see here. For example, a sphere is simply connected, a torus is not simply connected. Probably seen these words before. And our sense of topology and the connectedness will get realized when we define these in the mathematical logical way. The fact that the sphere is different from a donut or the cup is same as a donut is contained in the information about the path connectedness of these collection of points. It has nothing to do with the curvature or the differential geometry of these structures. If you look at the curvature of a cup, it's definitely different from that of a donut, but topologically they are same. So before we bring in the global concepts are captured in the definition of topology of a collection of points. And I'll stop here. If you have any questions, do not hesitate to ask. I will stop the recording so you